Alright, so in the last video we explored how to apply Dirichlet boundary conditions to solve the heat equation for a rod of length L. And in this video what we're going to do is we're going to look at a different type of boundary conditions called Neumann boundary conditions, sometimes called von Neumann boundary conditions. It's pretty much the same guy. So we have for Neumann boundary conditions, what it means is that we're given the values at the boundaries for the amount of heat that is actually passing through. So this the first derivative of u with respect to x, in this case, is the heat flux into the system along the x direction. So basically what this is telling us is that we have a heat flux of 0 at both ends, which means that we have a bar that is insulated at both ends, because if no heat is passing through or coming out, that means that the ends need to be perfectly insulated. Now obviously in practice you cannot really achieve perfect insulation, but you get the idea that assuming an ideal system in which there's no heat passing through on the boundaries or coming out of it, then we can set up boundary conditions like this one. And remember, because u is essentially just a product of two functions, we can set up the boundary conditions as this for a single variable. So what we're going to do now is we already have our three possible solutions, which we found through separation of variables. Now what we're going to do is we're going to solve them using these new boundary conditions that we have established, and hopefully we'll get a different solution to what we got last time. And that's the beauty of separation of variables. Once you have all your equations like this in the form of ordinary differential equations and you figure out what the solutions are, you can pretty much just choose any boundary conditions that you can think of, and that's going to give you a completely different solution. So it's pretty much like applying initial conditions to an ordinary differential equation, but here we have a lot more to work with. So let's get started and let's consider the first case. So let's have the derivative of x. In this case, it's just going to be a for this equation, and then 0 equals to a. Now obviously that implies a is equal to 0, and then equals to a. So we have something here that tells us that this is just going to be 0 in both cases. So obviously this is not a very useful solution, because we want an expression that tells us how the heat distribution along this rod changes over time and with respect to this space distribution between 0 and L. So obviously this is not useful, so we're going to discard that option. Now let's consider the second case. Let's find the derivative of that function first. So we're going to have a lambda square root of lambda e square root of lambda x plus b, oh sorry, it should be minus, right? Minus b square root of lambda e to the power of minus square root of lambda x. And now with this, what we're going to do is we're going to apply the boundary conditions. So let's get started with 0, 1. So this is going to be 0. So if we set this equal to 0, then that means that we're going to have a square root of lambda minus b square root of lambda. So this implies that because square root of lambda, we know that the eigenvalue is not going to be 0 according to the first case, which we just discarded. Lambda cannot be 0. So we're going to have the following case. We're going to have square root of lambda times a minus b equals to 0. So obviously this implies that the only way in which this can be true is that a is equal to b. That's the only way this equation can be satisfied. Given that lambda is not 0, then we need to set b equals to a so that this is satisfied. So we're going to assume that that's the case. And now we're going to apply the second boundary condition. So we're going to have, so if a and b are the same, we can pretty much just take our constant out of the equation. So we're going to have square root of lambda e L square root of lambda minus square root of lambda e minus square root of lambda L. And obviously I should have factored out the square root of lambda as well. But essentially what this is telling you, so let's write it this way. We have 0 here, we have a square root of lambda, and then we have these two constants here, Now obviously, because we know that lambda and neither lambda or L have a value of 0, then this particular difference here is not going to be 0, which implies that the only solution is that A is equal to 0, and that means that B is also equal to 0, so the whole solution is going to go to 0. So obviously we cannot use that, so we have to discard this solution as well. And now let's consider the third case. Let's consider the third case. We're going to have derivative of x that's going to be equal to minus square of lambda A sine lambda x plus square of lambda B cosine of lambda x. And now we apply the boundary condition, so we're going to have this one equals 0, and this is going to be 0, this is going to be 1, so we're going to be left with lambda times B. So cosine goes to 1, and then this implies, because lambda is non-zero once again, that B is equal to 0. So what this means is that we're going to look back at this equation, and B is going to be 0, so the actual solution is just going to contain the cosine term. So now let's apply the second boundary condition. Let's apply the second boundary condition, and we're going to have the following. We're going to have equal to 0, and we're going to take the same function, so that's going to be, well, where is it? B is equal to 0. So that means we're going to be left with this one. Okay, so we're going to be left with this one, so we have A sine L lambda, and that's pretty straightforward, because that implies that we know that A cannot be 0, so the whole solution would be 0, so we have to set L square root of lambda equal to n pi, where n is just integer multiples of pi, and so on. And once again, our eigenvalue lambda is going to have the following definition: n squared pi squared over L squared. And that implies that our solution for the space part, or the x direction solution, is going to be the following. It's going to be an, so the nth solution I should say, it's going to be an sine, or it should be cosine actually, cosine n pi x over L, because remember that we're using, since B is equal to 0, then this term vanishes, and we're left with this one. And so the total solution is just going to be the sum of all those terms. So we're going to have the sum of an cosine n pi x to infinity of n equals to 0. Okay, so I need to explain a little bit about what's happening here, and the best way I can do it is from a physical way. So if we put n equals to 0, we know that cosine is going to become 1, so we're going to have a0 is going to be a constant value, so that's going to be the first term in the sum. We need to account for that, so that's important to include. The reason we started the sum from n equals to 1 in the previous case, where we had the sine function here, is that we know that the first term was going to be 0 anyway, because sine of 0 is equal to 0. But in this case, we need to take into account the fact that there's this constant here, which is going to be the first term of this expansion. So that's why we started from 0. Alternatively, we could write this as follows. So let's write it as a0, which is the first term, plus the sum to infinity from n equals to 1 of an cosine n pi x over n. So that's essentially the same thing. And the reason we need to write it this way is because this is also going to be found using a Fourier series. So both this and these coefficients are what are called Fourier coefficients, and once we learn how to apply Fourier series, we will be able to solve this equation. So that's basically our solution for our function of x. And now for a function of t, we're going to have the same, because remember, we solved the case for lambda is less than 0. We found that this corresponds to the correct solution. So that means that t of t is once again going to be the same. So it's going to be e to the minus c squared n squared pi squared over L squared times t. And so the general solution to this equation, using those Neumann conditions that we introduced, is going to be sum from n equals to 0 to infinity of an sine, or cosine again. See, I keep getting confused with this. N pi x over L e to the minus c squared n pi squared L squared times t. So this is going to be the solution for an insulated one-dimensional rod that has the following boundary conditions, where essentially there's no heat flux on the boundaries. So hopefully these 3 videos have shown you a little bit about what the whole method of separation of variables works as, and why it is so useful for solving certain simple partial differential equations like this one. So we can have mixed derivative, we can have first and second, or just second derivative, or just first. But it is quite useful for certain problems that are very practical. So the heat equation, the wave equation, there are a few equations here that are used quite a lot. So we can actually apply this to a whole range of different problems simply by changing the boundary conditions and by changing the dimensions in which we're working. Because remember, the heat equation tells you everything you need to know about how heat is distributed in a material. And that c squared term, that's just some coefficient related to the material it is traveling through. So this little equation here basically tells you all the information you need to know about the system. And just by playing around with the boundary conditions and the initial conditions, you can pretty much model and simulate and even accurately find how the heat is distributed across a particular material. It doesn't have to be a rod, it can be a 3-dimensional shape or something like that. So separation of variables comes in quite handy when we talk about these cases.